Welcome to today's webinar, Deep Dive, Amazon Redshift for Big Data Analytics. Our presenter today is Zach Christofferson. Zach is a Palo Alto-based database engineer at Amazon Web Services. In his role, he assists Amazon Redshift users from all industries in fine-tuning their workloads for optimal performance. As a member of the Redshift service team, Zach also influences and contributes to the development of new and existing feature services. Today with us, we also have Tony Gibbs, Solutions Architect, Eric Ferreira, Database Engineer, Mara Kleider, Senior Product Manager, and Sushim Mitra, Database Engineer. There are webinar moderators who will be engaging with you and answering your questions throughout the presentation while our presenter presents. Zach, welcome. The floor is now yours.
All right, thank you, Ryan, and hello, everyone. Thank you for joining me today for the Amazon Redshift Big Data Analytics webinar. As Ryan said, I'm a database engineer on the Redshift service team based out of Palo Alto. I've been at AWS for about 2.5 years working with Redshift. I've assisted hundreds of customers with migrations and performance tuning, and today what I hope happens is I'm able to impart some of these experiences to you. So we'll start by briefly covering an overview of the service, discuss migration considerations, then dive into some performance optimization techniques related to table design, data ingest, and database maintenance. The second portion of the webinar is kind of a pseudo demonstration where you'll be shown how to go about identifying if your cluster is able to benefit from optimizations I share with you today. Just prior to the demonstration, I'll be providing a link to various materials which can be used to reproduce the steps I performed during the demonstration, as well as references to other resources that can be used to improve your current Redshift performance. So looking at the poll results, it seems like we have an audience with a pretty mixed experience with Redshift. So this is an advanced level webinar, and I won't be spending too much time on the service basics. So if you find that you need a refresher on these topics, please do stick around until the demonstration, as the resources that I'll provide at that time will also contain additional links to my favorite Redshift sessions, which range from basic to advanced content. So Redshift is our relational data warehouse service, and we've designed it such that it's simple, fast, and cheap. Now when I say simple, I mean that from a few different perspectives. From the perspective of an end user, it's simple in the sense that it's familiar. Data is accessed and manipulated using standard SQL from any of your favorite SQL clients or BI tools over standard JDBC or ODBC connectivity. But it's also simple from an operational perspective. We've automated the management of backups, scaling, patching, security, restoring, and recovery so that you can focus on your analytics rather than database administration. And Redshift is also fast, and I say that because we've optimized it for scans against terabyte to petabyte size data sets, which we've done by leveraging columnar storage, compression, and a 1 megabyte block size within a massively parallel shared nothing architecture. And it's also very cheap. With reserved node pricing, you can secure costs at $1,000 per terabyte per year on our HDD platform, and even on-demand pricing on our SSD platform is inexpensive, starting at 25 cents per hour, with SSD reserve node pricing as low as 9.4 cents per hour. So today we have customers from every industry that are leveraging Redshift. And here's just a small sample. Now whether it's NASDAQ, who's ingesting 5 billion rows daily to analyze orders, trades, and quotes, Yelp, which is processing tens of millions of ads a day and analyzing ad campaign performance or new feature usage, or a company like Desk.com, who exposes a Redshift backend directly via a user-facing portal. There are a number of use cases which can leverage Redshift. At a very high level, the architecture of Redshift consists of a leader node and compute nodes. So the leader node is provided free of charge in multi-node configurations, and functions as a simple SQL endpoint, handling query optimization and coordinating the parallel processing of the workload throughout the cluster. But the compute nodes do all of the heavy lifting. The table data resides on these nodes, and this is where it's actually processed in parallel during query execution before sending the results that's up to the leader node for merging and then returning to the client. And to take a deeper look into the architecture, we can see that each compute node is actually split into a number of slices. And these slices are a unit of data partitioning, which encompass the division of both data storage and data processing. Each slice is able to process a portion of the workload in parallel, and the number of slices ranges anywhere from 2 to 32 slices per node, depending on the node type. So when rows of data are assigned to a slice within a cluster, we're leveraging columnar storage rather than row-based storage. Now with columnar storage, we're optimized for scanning large tables, typically in patterns often requested by analytical workloads, such as performing aggregations over a given column. In a traditional row storage database, this would require the scanning of each of the row's values regardless of if it were relevant to the query or not. And in this diagram, blocks containing data which would be scanned in a row storage database are highlighted as orange. But in columnar storage, we can access only the column of interest and reduce the number of blocks needing to be scanned significantly. And also with columnar storage, we're grouping similar data physically near each other, which allows us to leverage various encoding algorithms for compression. And since each column can grow and shrink independently of one another, this allows us to save significant storage space to drastically reduce I/O. And compression in Redshift typically results in a 2 to 5x reduction in storage footprint, and this also translates to a 2 to 5x reduction in necessary I/O. In the graphic here, we can see that these columns are being sized independently based on the data profile, data type, and compression ratio. We also leverage what are called zone maps to effectively prune blocks from needing to be fetched by checking predicates against an in-memory block header, which contains the min and max values for that block. So for a range-restricted scan, if a block has a min-max range which doesn't include the relevant value, then that block is simply skipped without needing to perform any further work. These zone maps, along with sort keys, allow us to scan terabyte to petabyte data sets incredibly quickly, while processing only the data relevant to your queries. So I work with a large number of users who are migrating to Redshift from either an existing data warehouse solution, an OLTP solution which can no longer operate at scale for analytical workloads, as well as a number of startups who are getting into analytics for the first time and have chosen Redshift. Regardless of the previous solution, there are a number of factors to consider when leveraging a columnar data warehouse solution like Redshift. The first point that I'd like to stress is that forklifting, or performing a lift and shift from an existing solution to Redshift, is definitely possible in many cases, but will not result in optimal Redshift performance. There are many intricacies to Redshift schema design, and prior solutions often don't have comparable feature sets. So by performing a lift and shift, you're forsaking the features which set Redshift apart and allow for impressive performance at scale. So if let's say you're migrating from an OLTP system, you may have had significant concurrency requirements for your operational workload, perhaps ranging to hundreds or thousands of concurrent processes. Redshift as an OLAP data store is optimized for batch processing, so it reaches maximum throughput at a much lower concurrency. Now, we technically support a maximum of 50 concurrent processes, but we've actually measured optimal throughput for a typical OLAP workload at somewhere between 8 and 12 concurrency. And also in an OLTP data store, when you go to create a table, you can do so with minimal thought, since you can always create new indexes as needed to facilitate new reporting requirements. But in Redshift, there is no concept of indexes. We have what are called sort keys and DISTKEYs, or distribution keys. And these need to be defined upon table creation. So for this reason, it is beneficial to build your tables based on your reporting requirements initially, and putting a lot of thought into this up front. And while there are no indexes in Redshift, we do allow the definition of primary key, foreign key, and unique constraints, which are leveraged during query planning, but these constraints are not enforced. So if you attempt to load duplicate data into a primary key column, we will allow it. But if you're able to enforce these constraints, then I'd recommend defining them. I've tuned a few workloads in the past by adding appropriate foreign key, primary key constraints, and that's resulted in as much as a 50% performance improvement for certain dashboard queries. And on Redshift and this shared nothing MPP architecture, we are fully ACID compliant. We achieve this by offering a distributed two-phase commit process. And however, this process is much more expensive than a database commit would be in an OLTP database. So we do recommend batching together dependent statements and processing large amounts of data before issuing a commit to reduce the overhead otherwise introduced by frequent small transactional commits which write to disk. And along these same lines, blocks in Redshift are immutable, and we're needing to rewrite a number of partially filled blocks when you're issuing very small inserts. So issuing an insert statement for just a few rows is generally just as expensive as an insert of hundreds of thousands or even millions of rows. For this reason, we recommend using Redshift for analytical workloads only, and keeping any sort of operational workloads such as a job state tracking table and an external data store, which is better optimized to facilitate such an OLTP workload, perhaps something like RDS Postgres. And lastly, many common workloads benefit from partition table data by time. A standard use case is to add and drop partitions based on data retention policies, but table partitions do not exist in Redshift. Instead, it's recommended to use what are called time series tables to manually partition this data and append the tables together using a union all view on top of them. We have a number of optimization features for queries against union all views, so you will find that aggregations and filters will be pushed down to the underlying tables and the views automatically. So fixing a poorly defined schema is the way we see the most significant performance gains in Redshift. A change to a distribution key or sort key to facilitate a given query pattern can result in multiple orders of magnitude improvement. For this reason, it's important to understand the concepts of data distribution, sorting, and compression, and also know how to identify which columns to leverage with these table properties for optimal performance. So the primary goal of data distribution is to ensure that data is evenly distributed throughout the cluster for parallel processing. The secondary goal is to minimize data movement during query processing. Since each slice only has a portion of the table data, it's sometimes necessary to redistribute data within the cluster to facilitate various aggregations or joins. By distributing tables correctly, we can often avoid this movement and reduce the dependency on available node-to-node network I/O during execution, which allows us to scale significantly. So there are three options for data distribution: key, all, and even. Key distribution is specified on a single column in a table, and as data is ingested into this table, we take a hash of that column's value and distribute the corresponding row pertaining to that column's hash to a specific slice. With all distribution, we store a complete copy of the table on the first slice of every node. And for even distribution, we perform a round-robin distribution of the data with no attempt to store similar rows or values on a specific slice. So when it comes to choosing which distribution style is best for your table, generally key is the best for large fact tables that are joined with various dimension tables. If the table is not joined against, then you can still distribute on a column to localize aggregations. And this distribution style is also good if you're frequently deep copying or archiving a table with like an insert into select statement, since the copy will be performed locally when both the source and destination table share a common distribution key. All distribution is good for slowly changing dimension tables of a moderate size, but it's really important to test here, since too large of an all-distributed table will suffer from a lack of parallelized scans, and too small of a dimension table will not benefit since the cost of distributing such a small amount of data is very insignificant in Redshift. And then finally, even distribution is appropriate when there are no columns which would make an appropriate distribution key without otherwise introducing a skew or an unbalanced amount of data throughout the cluster. It's also appropriate for very small dimension tables. So the goals of sorting are also very straightforward. We're seeking to physically order data in a way which maximizes the effectiveness of the zone maps we discussed earlier. Sorting to optimize zone maps and then using a query which leverages them allows us to reduce the amount of necessary I/O significantly. And with sort keys, what you're really wanting to do is prune as many blocks as possible, which is dependent not only on the type of sort key, the sort key columns, and the column order, but also on the data profile and the query patterns. And in a few scenarios, there will be no obvious sort key combination, and it will require weighing your business requirements while testing various compound and interleave definitions to determine what is best for your use case. In other cases, it is much more straightforward, especially for typical workloads. A sort key is most often defined on a column used in a query predicate or filter condition. For many cases, this is a temporal column like a date or timestamp, or sometimes an identifier. If a table is not often filtered, but is instead grouped by a number of columns, you can sort on these columns as well to prevent the sort required for that group operation from occurring during the aggregation. And alternatively, if you have two tables that are joined on a common column, and these tables share a distribution key already, you can also sort these tables on the same column to facilitate a merge join, which is by far the fastest of all of the join types. But in practice, what we see is compound sort keys are being used as they're appropriate for most of the use cases that are on Redshift today. These are use cases where we're filtering on something like time series data, and you're typically issuing a number of queries which are defined with very well or clearly defined filter criteria. The alternative is an interleaved sort key, which applies equal sort weighting to all columns in the sort key definition. And this is more common for niche cases, typically queries which don't scan time series tables and don't have well-defined filter criteria. Interleaved sort keys also require a larger table before their benefit becomes more apparent. So just as a sort key is defined in an attempt to reduce disk I/O, so is compression. Optimal compression encoding is also specific to the data profile, but we provide an automatic compression feature which enables you to identify what's best for your data. You can either let the copy command decide what is an optimal encoding for you, or you can run an analyze compression command to return recommendations. Both processes leverage the same strategy, but the copy takes an additional action by recreating the empty tables with the recommendation, whereas analyze compression simply returns a recommendation response. We also provide a utility which does the compression analysis and rebuilds tables for you automatically. This is available on GitHub, and a link will be provided along with some other resources just before the demonstration portion begins. So for automatic compression analysis, what happens is we sample a subset of rows and brute force the optimal encoding by compressing the data in every possible way, one column at a time, and then comparing sizes and making a recommendation based on which encoding allowed the data to be compressed to the fewest number of blocks. This process is very expensive and increases in duration as the number of columns in your table increases. So it should be considered more as an ease of use feature and not something that's occurring regularly as part of any repetitive ETL. So let's say your use case involves repeated loading of data into empty staging tables where automatic compression analysis would be occurring by default. It's unlikely that your data profile changes significantly from load to load. And this means that we're adding a significant amount of overhead to this ingestion process only to get the same recommendations every single time for each and every load. If we already know what those recommendations are likely to be, then disabling automatic compression analysis and instead just using the expected encodings is very preferable. This can be achieved by specifying column encoding explicitly in the create table statement, or using a create table like statement to inherit the encodings from a previous staging table or a parent table. So another time to avoid automatic compression is when it's recommended on the primary compound sort key columns. So if you have a sort key column which compresses so well that it stores a massive number of values per block, since the smallest fetch we can perform is only a single block, we also need to fetch a large corresponding row offset in order to materialize the rows for each of the values in the compressed sort key block. By uncompressing the sort key column, we reduce the number of values per block, and subsequently reduce the size of the row offset, and this reduces the number of blocks fetched so long as your queries are performing an in-memory scan of the zone maps. Performance will improve even when filtering on a larger uncompressed sort key column. So loading data with a copy command, sourcing files from S3, is the fastest way to parallelly load your cluster. As you scale on Redshift and your ingest requirements move closer to real time or your quantity of data increases, it is critical to be aligned with a few pretty basic best practices that will ensure optimal ingest throughput. So here we see various ways to ingest data into Redshift, loading from EMR, loading from a remote host over SSH, DynamoDB, or even Kinesis Firehouse. That's all possible. But loading directly from S3 is the fastest way to get data into Redshift. During a load operation, a slice on a compute node is able to download a file from S3, and we begin a streaming decompression. We parse the data into typed data fields, distribute that data to other slices in the cluster, and finally write the data to disk. For a copy command, a single slice can perform this operation on a single file at any one time. So in this example here, we have a node with 16 slices loading one file. During this operation, only 1/16 of the cluster is active, and 15 of 16 slices are sitting idle with no file to load. So the simple recommendation here is to always load a number of files equivalent to the number of slices in the cluster. And this ensures that the slices are fully saturated and is necessary in order to reach maximum throughput for data ingestion. And finally, we're going to discuss how to go about maintaining and optimizing a database which is undergoing a sustained workload. So configuring your tables initially is the first step, but as you load data into these tables over time, you need to ensure basic maintenance is being performed to facilitate performance at scale. Without maintenance, you can easily run into issues like stale statistics, unsorted data, or even data skew. And without adequate insight into your workload, you can also encounter WLM queuing, or commit queuing, or even issues with database lock contention. So database statistics are used by the query optimizer to create an effective query plan. Without statistics, Redshift has no idea how large a particular table is. So if it chooses incorrectly, it would result in the redistribution of a potentially massive table throughout the cluster. It's recommended to design such that your tables have an accurate number of statistics, such that the query plan is accurate. And the frequency of gathering statistics with the analyze command is dependent on the query patterns and your load strategy. So for example, there's no need to gather statistics on data that you won't be reading. So if you have a job that's doing micro-batch loading every 5 minutes, but you're only running hourly reports, then you really don't need to be gathering any statistics until just prior to those reports being run. And then once you do gather statistics, it's most important to ensure that we have stats on the distribution key, sort key, and the columns referenced in the query predicates. You can also check for missing table statistics, and this is shown in a system view called SVV Table Info. The field is called Stats Off, and we'll get into more detail on that during the demonstration. So over time, tables can become skewed if unbalanced data is introduced into a distribution key. If this occurs, then the workload also becomes unbalanced, and the query completion time becomes bottlenecked at the slowest slice, or the slice needing to process the most data. This can also result in skewed data in flight, which can cause one node to spill temporary data to disk, while others are processing a minor result set or generally idle. Tables can also become unsorted over time if data is constantly being loaded in a style which isn't in sequential blocks. And this causes the data to exist in the unsorted segment of the table, where it can still benefit from the zone maps, but the effectiveness of these zone maps degrades if the data isn't truly sorted. You can use a vacuum or deep copy operation to sort and move the data from the unsorted table space to the sorted table space. And I'll be covering how to address both of these issues in the demonstration shortly. So by default, Redshift has a WLM configuration, or workload management configuration, which allows the execution of 5 concurrent queries. And this can be increased to as much as 50 concurrent queries. And that change is made by modifying a cluster parameter group. And it's useful to monitor the state of the WLM queues on a regular basis to identify when WLM queuing is occurring and to potentially increase concurrency to prevent it. Now there's a script on our GitHub project, Amazon Redshift Utils, and it's named WLM Apex Hourly. And this allows you to historically check peak concurrency requirements so that you can fine-tune your WLM to accommodate the demands of your workload. And a link to this script will be provided in the documents that I'll be sharing momentarily. We also discussed earlier about how we use a distributed two-phase commit strategy, which we leverage to remain ACID compliant. It's possible that when a cluster is flooded with an operational workload issuing numerous small commits, you can accumulate what is called a commit queue, or a pending of commit operations. And this is all exposed in a system table called STL commit stats in a field named queue length. It's best to maintain a queue length under 5 if possible. And if you find your transactions are waiting excessively long to commit, then it's recommended to look into offloading any sort of operational workloads or needless transactions, and then working to batch together dependent statements into larger transactions. The final topic, which can sometimes be involved in performance-related issues, is database locks. And in Redshift, there's 3 primary types of locks which should be understood. There's a read lock, which would be created by like a select, update, delete, a write lock, which is created by a copy, update, delete, or an exclusive lock, which is typically created by DDL, like a drop table, truncate table, alter table. Each of these locks are granted on a table, and we don't do any row-level locking. Read locks on a table don't block anything, but exclusive locks from proceeding on that same table. A write lock will block other write locks on that same table, as well as exclusive locks from proceeding. And then exclusive locks will block every other lock type, including other exclusive locks. So in the event of an ungranted lock, subsequent lock requests queue up behind it, and this can be observed if you were to issue like a drop table statement while a transaction was open that held a read lock on that table. The drop table seems to hang due to the ungranted lock, and all subsequent read or write locks will also be ungranted until that hung exclusive lock is granted. And all of this is exposed in a system view called SVV transactions, and this is a view you can use to identify processes which may introduce lock contention. And these locks are always released upon the transaction close, not at the end of the statement. So for phase 2 of this webinar, I'm going to be showing how you can identify if the optimizations we covered today are applicable to your own specific clusters. I've provided a link shown here, but it's not necessary to navigate to this immediately. I'll have this visible for the entire QA portion so that everyone has an opportunity to access the content. And if one of the Q&A moderators could put the link in the chat, I would appreciate that as well. So really understanding Redshift performance and optimizing throughput requires an understanding of how to derive performance data from the Redshift system tables. This enables you to see what's going well with your implementation and what needs to improve. So at a very high level, I discussed approximately 12 recommendations for optimizing performance on Redshift. I'm going to spend the rest of this time working through about 10 system tables queries and query results, describing how to interpret the results and how to take action on the feedback. All of the SQL that's being executed, as well as even more, is available in this link that is shared here. So this first query aggregates on a few tables: STL explain, STL scan, and SVV table info. And what it does is it identifies tables which have been scanned with filter criteria but have no sort keys defined. We display a substring from STL explain info, and through that we're able to see the columns the table was filtered on, which allows us to determine how we'd like to go about sorting this table if we were to add a sort key. For this particular result, for the customer table, there's no clear pattern in the filter criteria, as we seem to be filtering on, it looks like, 6 different columns from this customer table. So this may be a good candidate for an interleave sort key. If I knew that I didn't want to use an interleave sort key in this case and I was forced to choose a compound sort key, I would look at something like putting a sort key on C phone and C comment, as that would hit the filters seen here on rows 1, 3, and 5. Now here's a very different result set, but from the same query. And this time the pattern is very clear. We see that we're routinely filtering on sale item DT. Sometimes we're specifying a date literal, and other times we're specifying a timestamp literal. We would want to standardize this based on the column data type for the sort key column, since range-restricted scans are only possible when dates are evaluated against date literals or when timestamps are evaluated against timestamp literals. So based on this output, I would redefine the table with a sort key column on sale item DT, and I would rewrite my SQL so that it leverages like a date literal filter. So this next query accesses the same system tables, but is specific to identifying tables which are already defined with a sort key column. So what we're looking for here is if the tables are sorted, which is shown in the unsorted column, if the filter criteria matches the column name and data type as the defined columns in the sort key, and in this case it does. We're filtering on L ship date. We do, however, see one query which specified a timestamp literal rather than a date literal, and this resulted in a non-range restricted scan, which is highlighted with RR scan, a value of false. We can also see the impact of this since the next column over seconds. This particular query had to run for 150 seconds due to not leveraging the zone maps, whereas other queries which specified a date literal returned in sub-second response time. So this query is used to identify compound sort keys which have the primary sort key column compressed. Queries the PG catalog tables and is database specific. So you have multiple cluster databases. Be sure to run this in each. As a general rule of thumb, so long as you are issuing queries which allow you to leverage the zone maps, it should be fine to uncompress these primary sort key columns for a potential performance gain. This information is also visible in the SVV table info system view in a field called SORTKEY1 skew. Now this query number 4 accesses the same PG catalog tables, but this time identifies non-primary sort key columns which are missing column encoding. So tables which contain columns returned by this query should leverage the column encoding utility in our GitHub project, or analyze compression and then recreate the tables so that we effectively leverage compression, reducing storage footprint and necessary I/O. These results access SVV table info and STV block list. And what we're doing here is we're identifying which tables are skewed due to the choice of distribution key. And we're reporting skew in two ways here. First, there's a ratio of row skew, which is calculated as the slice which has the most rows versus the slice which has the least amount of rows. And then there's a calculation of storage skew, which is calculated as the slice where the table consumes the most storage space versus the slice where the table consumes the least amount of storage space. And then finally, we visualize the percent of slices populated, or how many slices in the cluster contain at least one row for this table. So having a percentage less than 100 here for larger tables suggests severe skew issues. And in cases where there are fewer rows in the table than there are slices in the cluster, this can be unavoidable. But the recommendation here would be to identify a more appropriate column for distribution, or if no better column exists, then to use even distribution for the larger tables and all distribution for the smaller dimension tables. In query number 6, I'm identifying copy commands which leverage compression analysis by querying STL query and STL load commits. The column here, comp sec, details how many seconds were spent performing compression analysis for the table. And the column load sec details how long we actually spent ingesting data. The percentage column details what percentage of the total load time was wasted by performing a compression analysis, if the analysis was in fact needless. As we can see in these results, many of these loads extend load time as much as 40x longer than needed because of a compression analysis phase. So the recommendation here would be to disable this automatic compression by explicitly defining the column encodings when creating the staging table for loads, leveraging the encodings generated previously. In query 7, we're checking to see if loads into a particular table are leveraging an appropriate number of files from S3. And the goal here is to load as many files into the cluster as there are slices, or a multiple thereof, and to keep file size between 1 megabyte and 1 gigabyte. The query groups on tables, so some of these tables have had multiple loads, but calculating the average, we see that we're typically loading either 4 or 2 files per load, which would be ideal for a cluster with 2 slices. However, these query results were taken from a cluster with 224 slices, so at best that cluster is only leveraging an estimated 1.8% of its potential ingest throughput. And if you have any workflows which process, delete, or update statements on tables in Redshift, those rows that those statements delete or update are only logically deleted and made invisible to readers, but they still exist within the table until a vacuum, deep copy, or resize operation occurs. Even though the rows are invisible, they still consume space, they're still fetched from disk when the table is scanned, and they're only filtered out at the end of query execution. So queries which are scanning a large number of these deleted rows like this generate an alert to a system table called STL alert event log. And what this query does is we're aggregating on those events and identifying which tables are reporting a number of errors with this cause, and then the recommendation is simply to vacuum or deep copy these tables to physically delete the rows. Data ingestion into a table with a sort key anytime after the initial load also causes the new rows to be added to the unsorted segment of the table, causing the table to be shown as partially unsorted. Sometimes these tables are actually locally sorted by appending time series data in sequential blocks, and if that matches your load strategy, then you can ignore this report of unsorted table data. But if this does not match your ingestion strategy, then you should resort heavily unsorted tables by leveraging vacuum or deep copy, such that your zone map's effectiveness improves. And some database operations will automatically gather statistics in Redshift, like a default copy command or a create table as statement, but otherwise statistics need to be manually gathered. So if you're missing a large number of statistics, then the query planner is unable to estimate accurate row counts, and this can result in a poor execution plan. By identifying tables which report as having a large percentage of rows which are missing statistics, then you can do a targeted analyze commands to refresh statistics on those tables. And this is the query you would use to do that. So that's the end of the pseudo demonstration and the structured webinar. I hope everyone found that useful. I'm going to leave this link up for the rest of the duration of the Q&A session, so feel free to pull this content. It has all of the SQL that was there. It has descriptions on how to interpret the results. It also includes a number of links to other webinars that I particularly enjoy. Also has links to all of our GitHub projects. Lots of good resources there, so I would recommend everyone download it. I'm sure you'll find something there that if you're using Redshift, it'll eventually benefit you in one way or another. So now I'm just going to pass this over to Ryan for a moment while I review the questions which came in during the session, and then I think we can dive into the live Q&A session.
Okay, thanks a lot for a great presentation. And now we're going to move into live Q&A. So I'd like to thank Zach for his time presenting and Tony and Eric for engaging with the audience throughout the presentation. On the left-hand side of your screen, you will see 3 poll questions. Please go ahead and take a minute to click on the radio buttons next to your responses and provide us with some feedback. We have about 20 minutes left, so please feel free to continue submitting questions, and we will start addressing some of those that have been submitted. We apologize in advance if we do not get to all of them. Okay, I'm going to hand it back over to Zach now. Zach, go ahead.
All right, thank you. Just waiting for some questions to be assigned. If I'm unable to get to all the questions today, then I apologize. If you do have a question that really needs answering that I end up not getting to, I recommend opening up a premium support case if you have a support contract, and they'll be able to escalate it up to me. You can just kind of name drop me, say Zach Christofferson. Or if you don't have a premium support account, you can go ahead and post it on the forums. I'm going to keep an eye on those throughout the end of this week, so if you have a particular topic and you're part of this webinar, just post on the Redshift forums and put webinar somewhere in the topic so I can make sure I see it. So let's see, the first question I have is from Dean Trejo. The question was, what database is being used in this example? So the demonstration I was using was on a Redshift cluster. I was using a SQL client called PSQL, which was originally made for Postgres, but it works just great on Redshift. It's an interactive command line client, so you can use it on Windows, Mac, Linux. It's very lightweight. I would definitely recommend it. Next question will be from Jeff Bertman. For the last script, the stats off column, Redshift knows which table statistics are stale for. Yes, it does. So we keep a running track of how many rows are in the table, and this includes deleted rows. But the statistics are stored in the PG catalog tables. So when you gather statistics, we update a column in PG statistics called rel tuples. And then we use a ratio of how many rows have statistics gathered for them from PG statistics, compare it to the total number of rows in the table, including deleted rows, and from that we get a kind of a percentage of how many rows actually have statistics. I have a question from Noor Ahmed. The question is, why does it skip the identity column when we try to load the data into an identity column? It sounds like you're trying to do a copy command into a table with an identity column defined, and you're observing that it's not auto-incrementing, right? That's how I'm interpreting the question. So it's important to note that an identity column isn't necessarily an auto-increment column. Since the tables are distributed across various nodes, the overhead of synchronizing how to increment a value for an identity column would need to be coordinated between nodes, which would add some overhead and result in a performance degradation. So with an identity column, the guarantee is that the value will be unique, but it won't, and it will be positive, but it won't necessarily be auto-incrementing or in order, since we are processing this ingestion in parallel on multiple different nodes and slices throughout the cluster. Next question from Gadavari M2. Is there intercommunication between compute nodes? Absolutely. So the Redshift clusters exist in a HPC room in the data centers. They're attached with a high throughput network connectivity. We broadcast data from node to node using UDP. So let's say you have a table that's distributed with even disk style, and you need to join it with another table which is distributed with even disk style. The inner table would need to be broadcast to all the other nodes in the cluster. So what would happen is each node would take its portion of the table and send it to each and every other node. And this can become a bottleneck if you're not leveraging things like disk style all or distribution keys. There's a lot of connectivity that occurs and data transfer that occurs within a cluster. And if it's not optimized and every single query is needing to rebroadcast massive tables, then it can become a point of contention. But by leveraging appropriate disk keys and distribution styles, you can avoid that and scale very, very well in Redshift. Next question will be from Aro Bindo Saha. Announced today during the quarterly update, Redshift became 2x faster, Vacuum has become 10x faster. Can you comment on these new improvements announced very recently? So there was some patch that went out probably 3-4 weeks ago now, and it included some improvements to query execution related to memory management, as well as some improvements to the vacuum operation. So before, the vacuum operation would need to rewrite a significant portion of the table when it was removing deleted rows, and we've modified it such that it's only rewriting the blocks which need to be modified now. So a 10x estimation is kind of modest. There's particular customers that have seen as much as 100x improvement in vacuum performance. But we've got a lot of good feedback about this. If you have any specific feedback on the feature, if you're observing any significant performance changes from this, I'd recommend you reach out to the Redshift PMs. We always like hearing these customer stories. Question from Dean Trejo. Can we use Tableau to read Redshift? Absolutely. It's one of the most popular backends for use on Tableau. It uses just standard ODBC connectivity to Redshift. Works very, very well. Question from Appadurai Subramanian. Is it a good strategy to go for update or prefer delete and insert? Really, it's the same thing. So in Redshift, an update will do a logical delete, and then it'll append a new row to the table. So if you can perform an update by scanning a table just once, and the delete and insert would require multiple scans, then the update may be slightly faster. It's really one of those things that's dependent on the nuances of the SQL and like the table schema that you're acting against. It's kind of hard to give a blanket statement here, so the best I can offer is to say you may need to test to confirm. But from what I've seen, depending on how many rows are being modified, an update would be fast in most cases. Another question from Adrian Rizzo. Have you seen clients using MicroStrategy as their UI BI tool for Redshift? Yes, very popular. Lots of customers use MicroStrategy. MicroStrategy has been great. They put out a really good document. I think it's like 70 pages long about how to optimize MicroStrategy in a way so that it really benefits from all of the features that Redshift has to offer. So I definitely recommend looking at that if you're going to be using MicroStrategy with Redshift. But yeah, it's one of the more common BI tools along with Tableau. We see it all the time. Question from Srini Puspala. Can we set up alert events on Redshift? What are the different alerts that can be set up? So you can absolutely set up alert events if you're familiar with like the RDS service. It's basically the same as that. So you can create an alert event on like a database, like a recovery operation, a resize operation, a backup. There's a whole list if you Google like Redshift event subscription. I think there's something like 60 different events that you can subscribe to, and then you can get notifications through SNS, you can get a text message, you can get an email, any of that. It's very easy, very straightforward. Question from Dean Trejo. What type of development environment or tool is typically used for Redshift and AWS? So what's great about Redshift is it's accepts standard JDBC, ODBC connectivity. It was forked from a very, very early version of Postgres, so a lot of the Postgres utilities and the Postgres drivers work just fine with Redshift. And you can really use any of the most popular tools out there. We already talked about MicroStrategy, we talked about Tableau. Agility is another popular SQL client. Looker is a popular BI tool. There's lots of great options, and they all work with Redshift. A question from Mike Holsworth. Is there an easy way to export data from Redshift to EMR or Hive? There is. So you can use an unload command, which will return the query results of your query in parallel to S3. So it's kind of like the inverse of a copy command. So you can dump the query results to S3, and then you can access those S3 files using Hive by pulling them into your EMR cluster. Question from Camille Patel. How easy is it to switch the location? I believe that this is asking how hard would it be to spin up an existing cluster in another region. So we actually make this pretty easy. You can configure what's called cross-region backups. So as you Your incremental backups are being taken on a regular basis based on how much data is changing. Behind the scenes, you've specified another region, and we're copying each of those incremental backups to this new region. So shortly after the backup completes, it's already in the other region, and then you just restore it from a snapshot as if it was any type of backup. And then after it's restoring, it'll take about like 5 minutes to come online, and then data will start streaming in from S3. Cluster is immediately available for reads and writes, but if you're trying to access some data which has not yet been streamed in from S3, those blocks will be prioritized, and that query will kind of hang until the blocks get there. But you can be ingesting data in another region in almost no time at all on Redshift. Follow-up question from W. Nagel. Cross-region backups are set from the console, the CLI, both. It's available on the console page. If you access like a cluster details page, there's 4 buttons at the top. It's one of those buttons. I think it says configure. I think it's under the backup button, but yeah, it says like configure cross-region replication or copy. Question from Jeff Bertman. Can we see the raw or uncompressed data size in a data dictionary view somewhere at the table, schema, or database level, not just overall percent compression across all nodes? So I'm not 100% on what the question is asking. I could interpret it 2 ways. Either you want to see how large your data would be if it was completely uncompressed, or you want to see how much data is consumed by uncompressed columns right now. If it's the former, that's not possible. We would need to kind of copy the data to uncompressed tables to get an accurate reading. But if you want to identify how much data is currently, or how much space is being consumed due to uncompressed columns, that's certainly possible. You can query SVV table info and join it with some of the PG catalog tables. There is a column encoding attribute on these columns, and there's an enumerated value which says that the column is not encoded. And using that, you could identify how much storage space is consumed by such tables. If you need help writing that query, feel free to reach out on the forums, and I can write it for you. It's not a problem. Question from Aman Thind. Is there a theoretical limit to the size of data that can be managed in Redshift? 2 petabytes right now is the theoretical limit. So that would be a configuration of 125 DS2 8XL nodes. We have many customers using configurations such as that. But right now that's the max on a single Redshift cluster. The customers that have requirements that exceed that are actually using multiple massive clusters like that. They do some federation of their tables throughout them to manage the large data set. Sure, I have a question to revisit query number 2. Let me take a look at that real quick. So query number 2 was identifying appropriate sort key to effectively prune blocks. Right. So in the second query, what we were doing was taking a look at a table which had a sort key, and then we were looking at how that table was actually filtered. And what we were trying to see is if the column that's defined as the sort key column is actually being used in the filter, and do the data types match, and is the table sorted or unsorted. In this case, it was. We're looking at L ship date. And it was a date data type. We were filtering it with date literals, but there was that one occurrence of a timestamp literal, which kind of invalidated the zone maps. And if you do download the zip file that I linked to, there should be a description there for that SQL, which better explains kind of how to interpret the results and how to use that query. Now a question from Jatsna Lakala. How do you export the database in Redshift to another database in Redshift, for instance, from dev to QA? So you can do this in a few ways. If you want to create a new cluster, you can actually just take a snapshot and restore. That would be like the most effortless way to do it. Another way, if you need to keep like a dev and QA cluster running in parallel, is you would just need to mirror the SQL, and then you could just unload all of the data from one cluster and copy it into another cluster. That's also a very common use case for customers who have like one cluster that they perform all of their ETL on, and then another cluster which just serves dashboard queries. So leveraging parallel copy and unload, you can do this very quickly. But if you have the luxury of being able to, keep or only fire up a dev environment as needed, then probably a restore from a snapshot would be the most cost-effective and the most effortless way to do that. All right, looks like we're reaching the end of our time. Thank you again. If I didn't get to any specific questions you had, as I said, feel free to reach out on the forums. I'll be watching that through Friday. If you have an AWS support account, feel free to create a case and reference me by name, and I'll take a look at any other questions I didn't have time to answer today. So now I'm going to hand it off to Ryan to wrap things up here.
Great. I'd like to extend another special thank you to our presenter, Zach, for his time and a great presentation, and also to Tony and Eric for answering the audience's questions. If you have any comments on our previous and upcoming webinars, or suggestions on the topics you wish AWS will cover in future webinars, please feel free to email us at aws-webcasts@amazon.com. Again, that's aws-webcasts@amazon.com. Your feedback will help us to improve our webinar programming. Thanks again to you guys, our audience, for taking the time to join us today, and enjoy the rest of your day.